Welcome to this workshop on Crosstalk cancellation systems, past, present and future. This workshop contains binaural audio. For the full experience, when you see this logo appear on the screen, please ensure you are listening using headphones or a Crosstalk cancellation system. We hope you enjoy the workshop.
Hello and welcome to this workshop. My name is Filippo Fazi, and together with my colleagues Jake Hollibon and Eric Hamden of the Institute of Sound and Vibration Research at the University of Southampton, we're going to talk about some of the basic theory and fundamentals of crosstalk cancellation, and we're also going to explore some of the most recent advancements in this field. As my colleague Jake already explained, we have recorded some nice demos for you, and it would be great if you could wear stereo headphones during those demos to enjoy the full experience. So let's start. This is the content of this workshop. We're going to first talk briefly about some of the fundamental localization cues like ITD and ILD, and we're going to give you then a short demo of stereo amplitude panning that probably you all know. We then cover some of the fundamental theory of crosstalk cancellation with some nice examples, and then we're going to dive a bit more into the theory of that and explore and investigate the stability of the two-channel crosstalk cancellation system. That will lead us to one of the most recent advancements, the optimal source distribution. And we're also going to look at the advantages when we start to increase the number of loudspeakers. So we're going to look into the three-channel crosstalk cancellation system, and also more in general, the use of loudspeaker arrays for crosstalk cancellation. We're also going to have a very nice demo for that. We're going to then talk about multi-listener crosstalk cancellation, covering some work done by Jake, and we're going to conclude with some of the most recent technology advancement in this field, which is the position adaptive crosstalk cancellation. Most of you are probably already familiar with this, but when we hear sound source, a single sound source, let's assume in free field that is somewhere in space, let's assume on my right hand side, then the sound is going to arrive first at my right here and later on at the left here. As a consequence of that, our brain perceives what is called an interaural time difference. In this plot here that you can see on the bottom left, you can see the interaural time difference in microsecond as a function of the angle, the azimuth angle of the virtual the source, of the real source. So of course at 0 degrees there's 0 ITD, and then it grows progressively and reaches its maximum when the sound source is at 90 degrees. This of course is just a simple model for the ITD for free field, a shadowless head model. It gets more complicated when we measure this with a real head. Then by convention we're assuming here that when the source moves to the left hand side, the ITD becomes negative. So this cue, the localization cue, the interaural time difference, is very effective at low frequencies. But also when the wavelength of sound starts to become comparable or even smaller than the size of the head, then the human head acts a very effective acoustic shadowing device. Henceforth, the sounds arriving at the right here, in this case, is going to be louder than the sound arriving at the left here. This generates the so-called interaural level difference, and this is another very useful binaural cue that we humans use for localization. So in this plot here, you can see as a function of frequency the interaural level difference between one ear and the other for different angles, 10 degrees, 45 and 90 degrees. And you can see that there is very little interaural level difference at low frequencies because the sound diffracts around the head, but then with increasing frequency and with increasing angle, the ILD gets larger and larger. So we humans use both ITD and ILD for sound localization. This is very effective for localization of sources on the horizontal plane, not so effective when we talk about elevation and front-back confusion. Localization in kind of full 3D space requires more advanced concepts like the head-related transfer function that we're not going to cover today. Let's take a look now of how stereo amplitude panning, which you probably all know, or you're all familiar with, is effective in terms of interval time difference. So I'm going to use these settings in various slides in this workshop. On the left-hand side, you can see a single frequency sound field. You can see here and here 2 sound sources, and here and here we have 2 microphones in free field that represent the ears of a listener. We are now assuming that there is we are using a shadowless head model, so there is going to be no interval level difference. On the right hand side here, we're going to see the signals driving the loudspeakers as a function of time, and below we're going to see the signals captured by the microphones again as a function of time. Let's play back. So as you can see, the 2 loudspeaker signals are in phase, and the left loudspeaker in blue here generates a sound that is louder than the right loudspeaker. What is really interesting here is that what happens at the ears, the signal captured by the left ear in blue is not significantly louder, if louder at all, than the signal captured by the right microphone. What is interesting though is that the 2 signals are no longer in phase. They were in phase at the loudspeaker, but at the ears they are out of phase. And this out of phase in fact defines an interaural time difference, which is the cue that our brain uses for localization with stereophonic sound. So an intra-channel amplitude difference at the loudspeaker maps into an interaural time difference at the listener's ears. It is now demo time, so please wear your headphones, and my colleague Jake and Eric will first of all show you the ITD and ILD when a loudspeaker that we're using as a source moving around dummy head, and later on we're going to see the effect of stereo amplitude panning. Enjoy!
Welcome to the Audio Lab, here at the ISVR, University of Southampton. For this section of the workshop, we will be demoing various loudspeaker arrays and looking in real time at how well they reproduce a virtual sound source. You might notice that the walls of this room are lined with loudspeakers, but we won't be using any of those. Instead, we will just be using the Genelecs set up to my right. Everything will then be recorded using a binaural microphone, like this Neumann KU100. During the demos, the audio that you hear on this video will be that of the binaural microphone, so make sure you listen with headphones on so you can hear exactly what the loudspeaker arrays are playing and how well they're performing. For the demos, we will be using the displayed Max MSP patch to both drive the loudspeaker array and to also analyse the reproduced binaural cues as measured by the binaural microphone. There are a few things to watch on this screen during the demos. The first highlighted area is a binaural encoder plugin from the free Visor production suite. This will be used to encode a source of pink noise into a binaural signal that will then be reproduced by the CTC loudspeaker arrays. When we demonstrate stereo panning, this plugin will not be used. Instead, a source of pink noise will be encoded using the stereo sign law with the position set by the highlighted input box. The next highlighted area is a spectral analyzer plugin, which lets us monitor the ILD as a function of frequency. Finally, the measured ITD and ILD are highlighted here. This ILD is a simplified metric based off of the RMS pressure between each ear. The ITD is calculated for low frequencies only and includes a simple mapping to a predictive virtual source position for demonstration purposes. During the demos, the video audio will be that of the binaural microphone, so you can hear exactly what a listener would hear if sat in front of the loudspeaker array. To demonstrate the max patch working, Eric will first walk around the Neumann KU100, holding a single loudspeaker playing noise. We can then see how the ITD and ILD changes, depending on the loudspeaker's position about the binaural microphone. We will now demonstrate how the classic stereo panning technique performs. The loudspeaker array will be a standard stereo pair positioned at plus and minus 30 degrees, and we will pan the virtual source not only within the loudspeaker span, but also outside of the span. This will then be measured using the Neumann KU100 positioned in the listening sweet spot.
You will have seen in this demo and probably heard as well that stereo amplitude panning is quite effective at reproducing the binaural cues when the virtual sound source is within the span of the loudspeakers, and to some extent when it's just outside of that span, but it doesn't work that well when the virtual image is located at a very, if you like, extreme angle, when it's 80 or 90 degrees to the left or to the right of the listener. Let's talk now about the concepts of sound focusing, constructive and destructive interference. Let's assume that we want to focus sound at this focusing point here in space, and we have two loudspeakers. In order to do that, we can work out the path difference between each loudspeaker and the focusing point, and then delay the loudspeaker this closer to the focusing point by an amount corresponding to the path difference divided by the speed of sound. By doing so, we can see that the farthest loudspeaker generates a wavefront first, and then the closer loudspeaker, and the two wavefronts interfere constructively at the position of the focusing point, therefore maximizing the energy at the focusing point. On the other hand, if we want to cancel sound at a given point in space, we can apply a similar approach, with the big difference that we need to phase reverse the signal of one of the two speakers. By doing so, and applying the same delays as before, we can see the two loudspeakers generate a signal in phase opposition that cancels out here at the desired cancellation point. And by tuning this delay, we can define the point in space where destructive cancellation occurs. Constructive and destructive interference are two fundamental concepts that are used in crosstalk cancellation systems. Let's talk now about crosstalk cancellation system. The ultimate objective of crosstalk cancellation system is to deliver binaural signal to the ears of a listener using loudspeakers. In other words, we want to deliver the signal intended for the right ear to the right ear of the listener only, and the signal intended for the left ear to the left ear only. Let's consider the setting in this figure. So let's assume we have a sound source somewhere in space, and that we record the signals at the right and left ear of an imaginary listener using a binaural mannequin, a dummy head, let's call it, and we obtain the binaural signal, let's call it U. UR is the signal corresponding to the right ear. UL is going to be the one for the left ear, and then we can use then a reproduction system consisting of two loudspeakers, and we can drive the right loudspeaker, with the signal UR, and the same we do for the left signal. Of course, the loudspeaker will generate a signal that will reach the right ear, therefore delivering the signal WR recorded at the ears of the listener. However, the signal intended for the left ear is not going to be delivered only to the left ear, but also to the right ear. This phenomenon is called crosstalk, and the objective of crosstalk cancellation is indeed to cancel this crosstalk. As a consequence of that, the right ear signal at the listener ear, WR, is going to be different from UR, the intended binaural signal. So what can we do to cancel crosstalk? Let's consider the setting. Here on the top left, we have the target binaural signal that is expressed in the time domain, and that corresponds to an ideal single pulse, click if you like, at the left ear and nothing at the right ear. On the bottom left, we see the signals in the time domain again, with which we're going to drive the two loudspeakers, the left loudspeaker and the right loudspeaker. Whereas on the right, we're going to see again in the time domain the two signals that are going to be recorded at the left and right ear. So let's generate a single pulse with the left loudspeaker. This pulse, of course, is going to reach the left ear. There we go. However, because of crosstalk, the left loudspeaker pulse is also going to be perceived at the right ear. What is interesting is that the two pulses, the left and right ear, is not going to occur at the same time, but because of the interval time difference, the left loudspeaker is indeed on the left. There's going to be a difference, a time difference, delta t, between the two pulses. In order to cancel crosstalk, what we can do, we can generate a pulse in phasor position, so a negative click if you like, with the right loudspeaker, with a little bit of delay, and because of that delay, that needs to be calibrated properly, the pulse of the right ear is going to reach the right ear, therefore cancelling the initial pulse generated with the left loudspeaker. This is the first fundamental step. How do we do that in practice in terms of signal processing scheme? Well, what we can do is we can take the signal intended for the left ear, play it back with the left loudspeaker, but also we can delay it, phase reverse it, and fit it to the right loudspeaker. Of course, the consequence of that, if we calibrate this delay properly, is that the signal intended for the left ear is going to be cancelled at the right ear. We shall of course do the same for the right loudspeaker. So it seems that we have solved the problem of crosstalk cancellation. But have we really achieved perfect crosstalk cancellation? Let's look at that again. The pulse generated with the right loudspeaker is going to indeed reach the right ear, but again, because of crosstalk cancellation, it will reach also the left ear. Therefore, whereas we're going to have perfect cancellation the right ear, the signal at the left ear is going to experience some sort of distortion. Indeed, the pulse in phasor position is going to arrive with a 2 delta t delay at the left ear. The consequence of that, if you look at the spectrum of the signal received at the left ear, which should be ideally flat, you can see here it's going to have all these notches. Indeed, the signal at the left ear is a comb filter. And of course, this corresponds to a significant quality degradation. So we need to do something about it. So let's do something a bit more clever. Of course, we can generate our pulse. The left ear is going to reach the left ear and also the right ear. As we explained earlier on, we can generate a pulse in phasor position that's going to cancel the signal at the right ear, but also is going to spill, if you like, leak into the left ear. So what we can do, we can generate now another pulse with a left loudspeaker that's going to cancel the spurious spike at the left ear, but obviously is going to leak into the right ear because of crosstalk. So we can generate another pulse in phasor position at the right ear, and so on and so on. We're going to apply a recursive process to cancel all the crosstalk. And this is what happens. What is really interesting, that in order to generate just a single ideal pulse here at the left ear, the loudspeaker needs to generate a lot of energy, if you like, most of which goes into destructive cancellation. This diagram shows how this method is implemented from a signal processing point of view. So the signal intended for the left ear feeds the left loudspeaker, but then the very same signal is delayed, phase reversed, and fed back, as opposed to feed forward as in the previous example, is fed back to the right loudspeaker. And the right loudspeaker generates a signal in phase opposition that cancels the component of the left ear signal that's spilled into the right ear, thus achieving crosstalk cancellation. Of course, we do the same for the other loudspeaker. We take the right loudspeaker signal and we feed it back after delay and phase reverse to the left loudspeaker. Therefore, for every pulse, every signal generated by the left loudspeaker, a corresponding signal in phase opposition is generated by the right loudspeaker, and vice versa. But as explained earlier on, for every little sound that we want to deliver to one ear, the loudspeaker needs to generate a lot of energy, all of which goes into destructive interference, into cancellation. In other words, the system is extremely inefficient. If we look at the spectrum of one of the two signals driving the loudspeaker, we can observe that it is anything but flat. It had some very clearly identifiable peaks. If you listen to that, it sounds very kind of ringing. Indeed, this is the spectrum of an IIR COM filter. And also, if you look here on the left-hand side, the signals here resemble indeed the impulse response of an IIR COM filter. This concept is better illustrated with this simulation. So what you can see here is again a horizontal cross section of a sound field. You can see here the left loudspeaker, the right loudspeaker, and this is a human head, again with a shadowless head model, the left ear and the right ear. We're going to try and deliver a perfect pulse at one or two ears, and let's see what the crosstalk cancellation system does. The right loudspeaker generates a pulse, and that reaches the right ear. What you can see here at the left ear, the two loudspeakers signals cancel each other out. And even though the intended signal was just at the very beginning, this cancellation process goes on for quite a long time. So let's now look at a bit of a mathematical formulation of crosstalk cancellation system. Here on the left-hand side, we have the binaural signal. We express everything in the frequency domain. So for a single frequency omega, the intended binaural signal is going to be a vector of two elements that we call U. Then the signal that is going to drive our two loudspeaker is going to be the vector V, again for a single frequency omega. And this can be expressed as the product of the target binaural signal U with a matrix, a 2x2 matrix, H of crosstalk cancellation filters. H11, H21, H12, and H22 are the elements of this matrix H, and they are the crosstalk cancellation filters. We are not using here, just to be clear, the feedback delay network approach that we looked at earlier. Then the loudspeaker signals are going to reach the left and the right here. We can express all the physical plan matrix, as it were, with this matrix C. In other words, the signal generated by the left loudspeaker, the transfer function between the right loudspeaker, if you like, and the right ear is going to be C11. Whereas the transfer function, the electroacoustical transfer function between the right speaker and left ear is going to be C21, and so on. Therefore, the signal W that's going to be recorded at the right and left ear of the listener, again at 2x1 vector expressed in the frequency domain, is going to be given by V, the signal driving loudspeakers, times the plant matrix C, representing again the effect of the loudspeaker, propagation in air, and if you want to include it, also the effect of scattering by the head. As we explained earlier on, V, the signal driving the loudspeaker, can be expressed as H times U. Therefore, W, the signal at the listener ears, can be expressed as C, the plant matrix, times H, the matrix of crosstalk cancellation filters, times U, the target binaural signal. Our objective is to deliver at the listener's ears a signal W that is as close as possible to U. The obvious choice here is to design the crosstalk cancellation filters in such a way that they compensate for the effect of the plant matrix C. So we can design the crosstalk cancellation filters H as the inverse of matrix C. In such a way, the product of C, the plant matrix, times H gives the identity. We include here also a delay e to the minus j omega delta, where this little delta is a time delay. We do that to ensure the causality of the crosstalk cancellation filters. If you didn't do that, then the filters H would be non-causal and therefore not reliable in practice. So again, this is the block diagram of our system. We have the target binaural signal. We have the signal W at the listener's ears. We have our crosstalk cancellation filters that we have designed by inverting the plant matrix. We do that frequency by frequency. And we apply also a modeling delay. What's going to be important is going to be the so-called path difference, R1 minus R2, where the R1 is the path, physical path between the right loudspeaker and the right ear, or equivalently between the left loudspeaker and left ear, also called the ipsilateral path, whereas R2 is the acoustic path in meters between the right loudspeaker and the left ear, or between the left loudspeaker and the right ear, the so-called contralateral path. R2 minus R1 is the so-called path difference, and that's going to play an important role. So we do this operation frequency by frequency, and in this way we can create our crosstalk cancellation filters using, if you like, a frequency sampling approach. We're going to explore now and investigate the physical causes of the system inefficiency that I have introduced earlier on. In order to do that, we're going to work in the frequency domain again, and rather than looking at the, if you like, effect generated by a single loudspeaker, we're going to look at the so-called modes, in other words, combination of loudspeaker signals. For instance, we're going to look at when the two loudspeakers generate an in-phase signal and when the two loudspeakers are going to generate an out-of-phase signal. So let's look at this animation here for the out-of-phase mode. You can see here the right and left loudspeaker generating signal out of phase. And this signal is going to be plotted here, the loudspeaker signals. And then we're going to see what happens at the left and right here, represented here by two microphones in the free field, again a shadowless head model. That signal is going to be plotted as a function of time here on the bottom right. Let's see what happens. Right, we see the two loudspeakers generate an out-of-phase signal, and an out-of-phase signal is captured also at the microphone position. A very similar thing happens with the in-phase mode. Now, the two loudspeakers generate an in-phase signal. It's very hard to distinguish here the left and right signal because they are identical, and an in-phase signal is delivered at the two ears, again in phase. So an in-phase mode at the loudspeaker maps into an in-phase mode at the ears if the system is symmetric, whereas an out-of-phase mode at the loudspeaker maps into an out-of-phase mode at the ears. And we can do this operation for every single frequency. But let's look now at a very special frequency. So we look at the frequency whose wavelength, lambda, divided by 2, corresponds to the path difference, R2 minus R1, that I have introduced earlier. In this case, when R2 minus R1 is lambda over 2, a very interesting phenomenon happens. Let's look at this animation. you can see that the two signals are in phase, and also both at the loudspeakers and at the ears. But what we see at the microphone signals corresponding to the ear signals have a very, very small amplitude. And we can clearly see it here in the sound field plot, because it seems that the two microphones sit into two nodal lines of the sound field generated by the loudspeakers. This is quite interesting, and is indeed the cause of the inefficiency that happens at very specific frequencies. The physical explanation of this phenomenon is quite clear. Indeed, if the path difference of R2 minus R1 correspond to the half wavelength, that means that if we drive the two loudspeaker with an in-phase signal, it arrives at each ear. These two signals arrive out of phase and therefore cancel out. At this frequency, the in-phase mode is extremely inefficient. In other words, we need a lot of energy generated by the loudspeakers in order to get a decent signal at the ears of the listener. This plot represents the mode efficiency as a function of the frequency omega multiplied by the path difference R2 minus R1 divided by the speed of sound C. The mode efficiency, if you like, is the ability of a loudspeaker mode, either the in-phase mode or out-of-phase mode, to transfer the energy from the loudspeakers to the ears of the listener. What we can see here, that at every frequency where R2 minus R1, the path difference, is an odd multiple of lambda over 2, we see that the out-of-phase mode is very efficient, whereas the in-phase mode is very inefficient. On the contrary, at those frequencies where the path difference is an even multiple of lambda over 2, like here, and also at 0 Hz, the in-phase mode is very efficient, whereas the out-of-phase mode is very inefficient. Perhaps not surprising if you consider at very low frequencies, if you have two loudspeakers and they create an out-of-phase mode, that's going to be pretty much a dipole and is going to be very inefficient at low frequencies. But this happens, as we have seen, at a number of other frequencies. And those frequencies where we have a significant inefficiency of either the in-phase or the out-of-phase mode, these are the frequencies where ringing occurs in the frequency response of the crosstalk cancellation filters that we observed earlier. We also see that at some other frequencies, the two modes have equal efficiency. So we've seen here that the path difference R2 minus R1 plays a very important role. And the path difference is, of course, a function of the loudspeaker span. This animation represents the effect of the loudspeaker span on the energy or the frequency response of the filters. Here on the right hand side, you see the two loudspeakers here at 10 degrees. When I'm going to run the animation, the span is going to increase. This is listen ahead. And on the left hand side, you see as a function of frequency, the efficiency of the in-phase mode, this dashed red line, the efficiency of the out-of-phase mode, the dashed blue line, and the solid black line represent the frequency response, the magnitude of the frequency response of the one of the filters. So what you can see here, that when the span is very small, just 10 degrees, we see that we require a lot of energy, the filters require a lot of energy at low frequencies to compensate for the inefficiency of the out-of-phase mode. We have a region here close to where the two modes have similar efficiency, where the frequency response of the filters have a very small magnitude, and then the magnitude rises again to compensate for the inefficiency of the in-phase mode. Let's see now what happens when we progressively increase the span between the two loudspeakers. As you can see, this ringing peak moves slowly towards low frequencies, and a new peak appears that corresponds to the inefficiency peaks of the out-of-phase mode here and on the in-phase mode. This goes on until we reach 180 degrees, which is the maximum loudspeaker span. That also corresponds to the largest possible path difference, R2 minus R1. So what we can observe is that ideally we would like to have a very good mode efficiency for both modes at every frequency, but this is not possible regardless of the loudspeaker span. On the other hand, we see that for a given frequency there is an optimal loudspeaker span. This plot represents the magnitude of the crosstalk cancellation filters as a function of frequency on the y-axis and as a function of the transducer span. And the color scale represents again the magnitude. So white represents low magnitude, whether dark represents large magnitude. So no good news. Ideally, we would like to be always in kind of low magnitude, because that defines a good efficiency of the system. We can see that when the span between the two loudspeakers is small, 10 degrees or so, we are in a bad situation at low frequencies. Then we have a region where we have low magnitude, so low energy, good efficiency, and then again, as we saw earlier on, poor efficiency at high frequencies again. With a stereo span here, plus or minus 30 degrees, so a span of 60 degrees, we see that again at low frequency we have an unideal situation, and we have a region when the energy is good, not too much energy, so good efficiency, and then we see an alternation across frequency of region with good efficiency, poor efficiency, corresponding to regions where both modes are equally efficient, or when one mode is inefficient and the other mode is efficient. As we have just seen, there isn't just a single transducer span that gives optimal results, optimal performance, optimal efficiency at all frequencies. However, we could decide to vary the loudspeaker span and therefore vary the path difference as a function of frequency. For instance, we could decide to use closely spaced loudspeakers at high frequencies and then progressively increase the span going down with frequency. For instance, at high frequency we could be here, so very small loudspeaker span and in the optimal region, and then we progressively increase the loudspeaker span as we go down with frequency. This is the concept of the optimal source distribution that was developed by Takeuchi and Nelson several years ago. By varying the loudspeaker span with frequency, we can achieve optimal performance, optimal efficiency at all frequencies. Technical terms, we can ensure that we are always here in this, let's call it, good efficiency valley. Of course, continuously varying the loudspeaker span as a function of frequency is a technical challenge, but solutions have been developed that achieve that, at least in an approximate manner. We've looked so far at two-channel crosstalk cancellation systems, and we have seen that we have recurring frequencies where the inefficiency of either the in-phase mode or the out-of-phase modes creates some kind of ringing in the frequency response of the filters. But let's see what happens when we increase the number of loudspeakers. The most obvious thing that we can do is to add one loudspeaker in the center. The central loudspeaker, of course, generates the same signal at the left and right ear of the listener. And as a consequence of that, we can say that the issue of the instability, of a lack of efficiency of the in-phase mode is completely solved at the presence of this additional loudspeaker in the center. This concept is more clearly illustrated by this plot. So we see the magnitude of one of the crosstalk cancellation filters in the top plot for a two-channel system and in the lower plots for a three-channel system. We can clearly see that the first peak, the third, the fifth, and so on, they correspond to inefficiencies of the in-phase modes. And these peaks are completely gone in the 3-channel system because, as I said earlier, the presence of the central channel solves the problem. So in other words, just by adding one loudspeaker in the right position, reduce by half the number of ringing frequencies. And this is a significant advantage. Jake and Eric are going to show you now another demo that demonstrates the effectiveness of a 3-channel crosstalk cancellation system.
The first CTC system we will demonstrate consists of just 3 loudspeakers positioned at 15, 0 and -15 degrees. This system will reproduce the binaurally encoded noise source, which will be panned around the listener position and measured by the Neumann KU100.
I hope you enjoyed the demo, and I'm sure you could appreciate that even though the span of the 3 loudspeaker was quite narrow, the crosstalk cancellation system was quite effective at creating the perception of a virtual image that was quite significantly lateralized up to probably 90 degrees to the left of the listener. So very effective crosstalk cancellation system with 3 channels. We have seen that just by adding one loudspeaker, the performance of a crosstalk cancellation systems improves significantly. But what happens when we increase the number of loudspeakers even further, like in the case of the figure here, when we have a 7-channel loudspeaker array? What happens when we try to achieve crosstalk cancellation with such a system? Well, having a large number of loudspeakers, we can start doing some beamforming. As you can see in the figure here on the bottom, these various loudspeakers, when we can be used as a phased array, if you like, and they can generate a beam of sound that focus the sound here on the left here. And just by doing that, the robustness of the crosstalk cancellation system is significantly increased. And we have better performance for crosstalk cancellation across frequency. And also when we use the system in a reverberant environment, because the beamforming approach creates such a tight beam of sound, depending of course on the number of loudspeakers we're using on the frequency, but in general we can achieve a better direct to reverberant ratio and therefore ultimately better crosstalk cancellation performance. So one could say the more the merrier. This concept is illustrated even better with this time domain simulation. As usual, we have here on the top the circles representing loudspeakers, and we have a shadowless head with the left and right here. What we're going to do now is to generate with all these loudspeakers an ideal pulse at one of the two ears. Let's see what happens. As you can see, the loudspeaker array is very effective at focusing the energy at the left ear, and little energy reaches the right ear. This concept can also be applied for multiple listener, for example. In this example that you can see, this picture represents a 3-listener system where each listener has a dedicated array. The fact that we are using loudspeaker arrays increases, of course, the directivity of each single device and reduces the leakage of sound from one listener to the other. In everything we have discussed so far, we have assumed that a single listener, is sitting still in the so-called sweet spot. But what happens when the listener moves away from the sweet spot position? Well, the effect of the crosstalk cancellation deteriorates very, very quickly as the listener moves away and the 3D image is completely disrupted. Can we create a system that is robust to listener movement? We can do that by including a camera, and that we can use to track the movement of the listener. This is one of the latest development in crosstalk cancellation technology, a listener adaptive crosstalk cancellation system. In this animation, we see on the top these black crosses representing loudspeakers, and these two stars here represent the left and the right ear of a listener. The red and blue patterns that you see here represent respectively the radiation pattern of the beam that delivers the sound to the right ear. For the red pattern, you can see this is the main lobe and a number of side lobes, but there is a minimum of the radiation pattern in the direction of the left ear, whereas the blue radiation pattern represents the pattern of the left ear beam that has a maximum here in the proximity of the left ear and a minimum close to the right ear, with a number of side lobes, which are typically of array beamforming. But the key thing now is that when the listener moves, because we track their position with a camera, then also the signal processing apparatus adapts in real time and keeps delivering a consistent 3D image regardless of the position of the listener. Again, we can achieve that because of listener tracking with the camera. The method I just described to you is at the heart of Audioscenic technology. This is a combination of loudspeaker array technology and listener tracking that is achieved with the use of a camera that you can see mounted, for example, in this prototype. The combination of the two, together with a powerful algorithm for adaptive crosstalk cancellation, allows for a consistent delivery of 3D audio regardless of the listener position. This allows to overcome the issue of the sweet spot. We're going to show you now the last demo for this workshop, where we're going to demonstrate the effectiveness of this position adaptive crosstalk cancellation technology. I should thank our friend Marco Simon Galvez, the CTO of Audioscenic, who helped us set up this demo. Enjoy.
The next CTC system we will demonstrate is a 5-channel loudspeaker array produced by Audioscenic. This array includes a camera mounted on the top, which is used to track the position of the listener. This information is then used to move the crosstalk cancellation sweet spot to be wherever the listener is positioned, allowing the listener to move freely around the loudspeaker array. To begin with, we will turn the listener tracking off to demonstrate that the crosstalk cancellation doesn't work when the listener is outside of the sweet spot. Then, we will turn the listener tracking on to show how this array overcomes this issue by moving the sweet spot to wherever the listener is positioned. For this section, we will no longer use the Neumann KU100 binaural microphone. Instead, Jake will wear a pair of DPA in-ear microphones so he can move around to demonstrate the listener adaptive CTC.
That was quite impressive, wasn't it? I'm sure that you could hear that the sound source was moving, the virtual sound source was moving all around you. And then when Jake moved to the left or to the right and the tracking system was off, you could have probably heard, and certainly will have seen in the ITD detector, that the image would kind of shifting back to the sensor where the loudspeaker array was, and so the 3D image was destroyed. But when Jake did the same exercise, but with the tracking system on, when he moved, the virtual image remains to his left. It moved a little bit when he was moving, but fundamentally stays, I think it was at 35 degrees. So that was again achievable because of the combination of loudspeaker array and tracking system. I'd like to conclude this workshop with talking a little bit about possible future developments of crosstalk cancellation. First of all, what we've discussed so far assumed just a single listener, and extending crosstalk cancellation to multiple listeners, likely using arrays of loudspeaker, is certainly an attractive perspective. Also, we have assumed that the listener does not move their head, but using listener tracking, we could also track head rotation and rely also on dynamic cues, which I haven't discussed, but dynamic cues are quite important, especially to overcome the issue of front-back confusion, and we use them also to determine elevation of sources. Again, we could think about controlling dynamic cues and adaptive crosstalk cancellation algorithm using head rotation tracking. Also, another challenge is the miniaturization of crosstalk cancellation system to be used, for example, in combination of laptops or perhaps even with mobile phones. This is of course difficult because obviously the audio range is a fixed wavelength range, and when we go down in frequency, wavelength becomes very large, so it is very difficult to achieve directivity even with a loudspeaker array when the latter is much smaller than the wavelength to be reproduced. So this is a challenge indeed. And last but not least, we have assumed now that so far that we're using it just a single, if you like, array, but we can think also about using multiple arrays, multiple systems distributed in an environment, and use the combination and interaction of them to deliver effective crosstalk cancellation and 3D audio to multiple listeners who are moving in this environment. Certainly a very attractive technical and scientific challenge. I would like to thank you very much for your attention. I hope you enjoyed this workshop. By all means, please do get in touch with us. You can see here our emails. And please do visit also our virtual acoustic and audio engineering website, who's dense with a number of other interesting technology we are working at. Thank you very much, and goodbye.